Hello, everybody, and welcome back to the Math and Physics podcast. I'm your host, Parker.
And I'm Ray, and we welcome you to episode 25, where today we have one of our professors, one of our other professors from our first year in physics, Dr. Paul Kushner. Do you want to talk a little bit about what you do at the University of Toronto, and what you teach?
Sure. Thanks, Ray and Parker, and thanks very much for hosting this podcast series and getting the word out about math and physics.
Awesome.
So
Thank
yeah,
you.
I'm a professor here at the University of Toronto. I'm a proud member of the Department of Physics. I've been here since I guess it's almost 17 years now, 2004, and I've been working on faculty in the area of Earth, atmospheric, and planetary physics. So there's a whole research group devoted to understanding the Earth and its atmosphere, and also the oceans and the interior of our planet. My focus is in the area of atmospheric and climate science. I do a lot of work trying to understand how the atmosphere works and what's called the circulation of the atmosphere, and also how climate change will impact the atmosphere and our own climate at the surface where we live. And I do a lot of work as well in understanding sea ice and snow and how those affect our day-to-day weather and climate. So I do a lot of work in that area using computer simulations, and also I do a lot of observational analysis. And all this is through a research group I have of undergraduate and graduate students and postdoctoral fellows. And we all work together on really interesting research projects.
Wow, that's really cool.
That's absolutely fascinating. And yeah, we'll have more questions later about your research group, but just to kick it off, we have this question that we ask all of our guests, and it is, what got you into physics in the first place?
I really started getting interested in physics, I think, as a student in Ontario, growing up in Ottawa. And I got interested in these ideas, kind of mysterious ideas about particle physics and high energy physics and their philosophical implications. I think that is common for many of my colleagues. And at the time, I just thought, oh, this sounds so interesting. And I enjoyed math and physics, and starting in grade 12 and then in grade 13, which is something that hasn't existed for a while, I had some really great teachers, and that really got me going. And having that good grounding in high school with calculus and physics, and doing a little bit of reading, and then really understanding the field. That's how I got started.
Awesome. Yeah, that's funny you say that you're from Ottawa because I'm also from Ottawa. I didn't know that about you, but yeah,
What was your high school?
Oh, I went to Franco West.
Okay. You don't have to include that in your final edit.
That's okay. I was gonna say, yeah, I'm actually doing my whole second year online from home, and yeah, I'm just gonna be staying in Ottawa for the whole year.
Right. No, that's good.
Yeah.
Well, I guess that's the part of the reality that you guys are facing now, is having to kind of reinvent what education looks like. We're all doing that together right now, and I think it's a pretty challenging undertaking.
Yeah, it's going to be as challenging for the professors, I'm sure.
I know online must be hard for the professors, right? Like, because the entire syllabus, well, I don't actually know. Would the syllabus be similar, or are you guys taking like a different approach?
To be online, generally speaking, or with the first year courses that you took with me last year?
Let's say the first year courses. For example, 151, 152. Is it like a similar approach to last year? Or are you guys taking something else because it's online? Are you guys doing something else? Like same topic, stuff like that?
It's going to be the same topics. So Professor Julian and I are teaching it again. And we are taking a similar approach for the lectures. Of course, it will be online. There will also be in-person components. At least that's what's planned right now. So we'll have a small group of students in our synchronous lectures, which will also be broadcast online. What I'm doing differently this year, the content is the same, but we're actually doing a lot of pre-recorded lectures that we want the students to listen to before they get to class. And some of the details will be presented. Actually, the plan is for a lot of the details to be presented in those lectures. I'm going to see how they work. I've pre-recorded a few lectures now. That's different because that gives us more time in class to talk about, problems, like solving problems, and also exploring ideas a bit more deeply, spending more time on demonstrations. So there is a bit of an opportunity to do what you guys probably know of as like the flipped classroom model, where students come to class with a good understanding of what the topic is, because they've done some exercises before and they've listened to some materials before, and then that gives us a chance to explore a bit more in depth. What's going to be really different is having the students, most of the students, like 90%, will be online while the live class is going on, and that's going to be a challenge. The topics will be quite similar. What's going to be really different is the fact that this year we'll only be running our practicals online only, so there won't be a chance to in-person labs.
Oh, because 244, which is Practical Physics 2, which is what I'm taking next year, actually forces people to go in person.
Yeah, that's 224. That's
right.
Yeah, 224. Yeah.
So the first year physics, I guess, just doesn't.
That was none of these decisions are easy. 224 is a practicals course, and so the decision there was really clearly focused on without an in-person component, it just can't be a lab, and we can't. There aren't ways of making this pedagogy work at home. Whereas with practical physics for the first year, it's I would say the labs are a little easier, right? They're more basic concepts, and so we felt that there just wasn't enough of a reason to bring even a small group in, and plus it's really hard to do the logistics. So the department focused on getting the second year students and the advanced labs, which are in the fourth year, running in person, because it's you just can't take that equipment home, and so they're doing it. I'm confident they're doing it as safely as they possibly can, with everybody's safety being the first concern. But it is an in-person type of experience for those courses.
Oh, awesome. I think first years are still gonna have a little bit of fun, not as much as we did, but hopefully a little bit.
For the flipped classroom model, we actually had that for Mat 137. Okay. They have like a whole playlist of basically every single topic on YouTube. We would watch the playlist and then go to class, and then in class we would just do exercises and ask questions and just go deeper into our understanding of the material.
Right. And how did that work for you?
I liked it, but I feel like I prefer going to class and actually learning the material and having like a professor just explain it in front of me. I preferred that, but it still worked, the online videos.
Unfortunately, because of the pandemic, it's kind of hard to it's kind of a special case scenario. But if hopefully, to be honest, I would prefer them teaching it, because I just think someone teaching it live is always better than watching a pre-recorded video, and I think I think everyone can relate with that, because watching someone talk about it is a lot more inspiring than just listening to a recording, right?
Yeah.
So I think that can make a big difference, but again, because of the pandemic, not really much we can do, unfortunately.
Right. Well, we will have a live class, and my decision was to try to pre-record more of the material, and that's the decision with Professor Julian as well. We'll see how it works, right? We'll see how the learning goes. I'm hoping that our in-person meetings will actually be really kind of quite enriching, especially for 151, which has a lot of the material that is covered in high school curriculums anyway. It's more, 151 is more of an experience of getting everybody on the same page. 152, I agree that we might have to revise, the approach for 152, because some of the stuff we talk about in 152 is really, it's hard, it's fields and things like that. So we'll see it.
To visualize, without
it's hard to, visualize, sit down and write things out. So, but we'll see how it works. Everybody will be getting used to the new reality, or the new normal
soon enough. So one question that I have for you, that I've always wondered, because before coming to U of T, my view of physics was kind of narrowed, in the sense that I didn't really think there were crazy amount of subjects, crazy amount of topics. But then I came and I heard that my professor is a teacher in atmospheric physics, and that's where you have your PhD, correct, in atmospheric physics?
It's a PhD in physics with a specialization in atmospheric physics. That's right.
Yeah. So my question is, why atmosphere? Like, what pushed you towards finding the physics about, or like figuring out the physics behind the atmosphere?
I think for me and for a lot of students who go through a physics program, your view coming in of what you find really interesting, and then what you learn about as you go along, really changes. So for me, I think a formative experience for me was going through physics and taking those courses that had a lot of interest. Special relativity, quantum mechanics, getting exposed to all those ideas, realizing where my strengths were, and then also realizing that there are ways of applying physics to all sorts of systems in the physical universe that extend from the very, very small to the very large and the in between. And I kind of like the in between, where we deal with the atmospheric and earth science. We are dealing with what we see every day. And I remember sort of being on a camping trip and sort of thinking, looking at the sky and clouds and thinking, I could study this. And I knew that there was really good work going on in the Department of Physics. Part of it is luck, I would say, too, because our department has the good fortune of being quite large and also quite broad in its scope. Our atmospheric physics group and the geophysics group go back to the founding of the department practically. So they go back several decades. Most places, most physics departments don't have such a kind of broad range of topics that are covered. So I consider myself very lucky to be here. And also I did my undergraduate at U of T too. So I was very much, influenced by the faculty here. Getting exposed to atmospheric science courses was part of my decision to kind of pursue this as a career.
Yeah, that sounds super interesting. When you say you're on a camping trip and you look up at the sky and at the clouds, for me, in my experience, I would look past the clouds into the stars.
Exactly.
That's I'm actually doing a specialist in astrophysics.
Right.
Yeah, that's why I say that, because I'm going to be taking the astronomy courses as well as the physics courses. So that's what interests me. But yeah, I also see why like the atmosphere and the geophysics aspect, or kind of branch of physics, would be super interesting to study.
Yeah, and now in astronomical sciences, it's all coming together because there's such a focus now on exoplanets and their dynamics and their atmospheres and their geophysical properties, like trying to understand. So we have our own solar system to turn to for analogies, and including our own Earth, and then we have the rest of the universe to look at and contemplate how planets behave in those other systems that we can see. So there's a lot of unity across the astronomical and Earth sciences as well. If you look at an organization like NASA, they have Earth observations as well as, of course, their space missions that go to other planets and that observe distant galaxies. So I really think in a department of physics, you get to see the whole gamut, and that's what's one of the great things about being part of this community.
Yeah, awesome. So for our next question, I just wanted to ask you about your PhD thesis. Can you talk to us about what you were studying and what you wrote about?
Sure. Okay, so my PhD thesis was an application of ideas in classical mechanics. That's a course that you're going to be taking, I guess, in a year or so. So in your classical mechanics courses, you start to look at formulations of dynamics that involve understanding the Lagrangians and Hamiltonian structure of dynamics. And it turns out that you can apply those same ideas to understanding fluid systems, and the atmosphere is a fluid. And so we have ways of looking at the atmosphere, treating it like a big swirling fluid swirling around our spherical Earth, and making approximations that actually help us deal with the math and so on in a way that actually stems right from classical mechanics. So my thesis was all about understanding a certain type of model system that was a good model for atmospheric dynamics. And I did a lot of math. It was a lot of mathematical physics, actually, but looking at the stability of the atmosphere and the way waves propagate through the atmosphere. And I'm talking about atmospheric waves here, like the movement of air, and trying to understand how that relates to kind of more the fundamental structure from fluid mechanics. And it was very theoretical. Actually, I had no computer graphics. There were just a couple of figures, a lot of math, a lot of variational calculus. And so it was it was quite an adventure. I really enjoyed it, and I learned a lot. Got to meet a lot of good people that way too.
Yeah, it sounds like a lot of long nights.
It was, yeah, but it was fun, especially once as a grad student. Once you get kind of get going, then so you're on a path of discovery, and you're learning things that nobody else knew before. It's really cool.
That sounds really cool. And talking about an atmosphere as fluids, I have one question that I've always wanted to ask someone who is in this field, but we've never really had anyone on. So now that we finally have you, I really want to ask you a question on turbulence. And you've probably definitely heard of the Navier-Stokes equations, one of the Millennium problems, which describes turbulence in the air, or at least that's what I think. So I'm just trying to grasp a better understanding of it, because it's been this millennium problem. It's this big thing that's never been solved. So maybe could you explain it a little bit further? Like, what exactly is the Navier-Stokes equations, and why can't it be solved?
Yeah, and what makes it so complicated?
Yeah.
Sure. Well, maybe it's worth thinking about what you're going to be learning in your second year course coming up. I think if you're taking 254, so there's the second year classical mechanics class. They deal a little bit there with nonlinear systems and chaos, right? And so what you learn as you start to study more math and physics is that there are systems that that can be solved with pen and paper and computer kind of in a straightforward way. And those are called integrable systems that have a solution that you can determine either directly through integration on pen and paper, or maybe with a simple graphing calculator or something like that, without too much difficulty. And then there are systems that just can't be solved that way. And it turns out that even very simple systems, maybe you've heard of the three-body problem, which is the problem of three mutually interacting particles under their own gravitational influence. So that problem turns out also to be what's called non-integrable. So even though it's super simple, just three particles, you can't find a closed form solution, and so your only choice is to solve it on a computer, solving the differential equations numerically. So it turns out that like the three-body problem, most problems are actually non-integrable for real systems in the real world. And so sadly, that's the case, although it makes the world much more interesting. The world is not very predictable, right? Including our solar system and so on. So even though our solar system is really super predictable in a way, actually you have to be really careful with what makes it non-integrable. The main thing that makes it non-integrable is a property of nonlinearity. And that nonlinearity means that you have that there's no simple solution that you can kind of introduce and then build up from to kind of get complicated solutions. So most fluid systems are highly non-integrable, all right? So there are a few fluid systems that we know the solutions for, usually ones that have that are really sticky fluids that are really damped, like a lubricating oil in an engine or something like that. That's a really, really viscous system. You can solve some cases for that, but most systems, which are what we call high Reynolds number systems, so anything that has that goes pretty fast, or where the viscosity is pretty weak, those tend to be very even if they're laminar and they don't have much turbulence in them, they're really hard to solve for. So when you ask about turbulence has all sorts of issues, right? So it's the Navier-Stokes equations are the ones underneath the whole system, right? And we've known them for going on, a century and a half or 2 centuries now, and we have a really good understanding of why of the equations themselves. But solving them is something you can't do except with a computer. And often what we do in fluids is try to make approximations to come up with, some special cases. Turbulence is hard because we don't, all we have is experimental evidence, looking at wind tunnels and looking in nature for the statistical properties of turbulence. And we know that turbulence involves interactions across many, many different scales of motion. So if you look up at a cloud, you see a big cloud, but then you can see that there are ripples in the clouds and there are small eddies in the clouds, and they're always changing in time. All those features are pushing each other around. So it's incredibly nonlinear because fluids advect their own fields of motion and carry their own information through the velocity field. So in the end, we can tell almost right away, a mathematician can tell almost right away that fluid equations are non-integrable and really, really hard to study. So, but all is not lost, because turbulence is it's a statistical theory, and we can tell a lot about the characteristics of turbulence by looking at what the equations depend on and what they don't depend on, right? So you can make some pretty good approximations that will tell you, for example, that the turbulence, say in a broad plane, like if you're on the prairies, the turbulence will look pretty similar from one place to another, right? So that's a big simplification, right? So that's called a symmetry, right? Because the turbulence is similar no matter, even if you shift around, do a translation, right, or rotate around. If it's isotropic, you won't notice a difference, particular direction to the turbulence. So you can actually make a lot of approximations that are very reasonable. The big mysteries in turbulence are things like, are like little eddies and swirls the most important thing, or are there big coherent structures that kind of that you can see, like vortices, that kind of govern all the turbulence? So turbulence is it's a big field, of course, in engineering and also in physics. And it's not one. It's really we're not going to find a solution to turbulence. Like, it's going to be more than a millennium problem because it's intrinsic. Like, there's a real limit to the solutions that we can obtain. But there's a lot we can learn about turbulence, and that's really what atmospheric and ocean science is all about: is learning what we can about turbulent systems, even though we have limitations. I don't know if that answered your question, Ray.
Yeah, I think that answered it quite well, for sure. Thank you.
Love to hear myself talk. So
yeah, no. Thank you so much. Thank you so much for explaining it so well. Yeah, I mean, for sure, because I did not have a very good understanding of it, and suffice to say, you explained it very well. Thank you.
Sure.
Yeah, I was gonna say that I forget the term, but I know that turbulence is very similar to a double pendulum, in the sense that initial conditions vary, like the kind of the end game, or kind of let's say, like the initial velocity or the initial position and the angles and everything, it will change the outcome so drastically that it's basically impossible to just solve those systems like generically.
Exactly, yeah. It turns out for the double pendulum case that you have two angles to solve for, and you have two angular velocities to solve for, and they're all coupled together non-linearly. And so those are the ingredients for sensitive dependence to initial conditions, or chaos, or that's one of the hallmarks of chaos. And also, with pendulums, you can sort of get really nonlinear behavior if you start a pendulum upside down, right, and just give it a little jiggle. It'll go unstable, and it'll fall one way or the other, and that's kind of unpredictable. When you add a second pendulum, that really makes it unpredictable. And so start two pendulums kind of in the upside down position, and that are coupled together, and they'll do all sorts of crazy things, as you've probably seen at the Science Center and so on. They have those kind of demonstrations, and that's a really good analogy for some of the things that can happen in the atmosphere. In fact, the person who discovered kind of the chaos in the modern sense, his name was Ed Lorenz. He was an atmospheric scientist at MIT who discovered that a very simplified atmospheric system with just three variables exhibited chaos. And he made that discovery using a computer, basically, and also thinking really deeply about the problem. And so he's the one who discovered this butterfly attractor that is the hallmark of his three degree of freedom system, the Lorentz system. So you can, if you haven't heard of that, you can look it up. And that was an atmospheric scientist. That's a point of pride for us.
So is he the same Lorentz from the Lorentz transform or no? Right?
That was Lorentz. So
different Lorentz. Okay, sorry.
Ed Lorentz was a different generation, and he died a few years ago. He's Lorenz, and his discovery kind of was it was made by an atmospheric scientist in the context of atmospheric science, but of course it applies to many different areas of study. Yeah, for sure.
So talking about that's basically what we're talking about, atmospheric science. Now we can finally, I think we've got a good enough base to get into your group, the Kushner Group, or at least,
sure,
right?
Yeah.
And what you guys really do. Because I've been doing some research, and I found out that you guys are basically a group of people doing research on the atmosphere, right?
Okay. Yeah.
Yeah. So maybe you want to describe it a little better than I just did.
Yeah. No. Well, you've got to start simply, right? So you just laid it out. We do research on the atmosphere. The atmosphere is part of the climate system, which includes atmosphere and ocean and land and ice and snow. And when we study the atmosphere, there's all sorts of questions we can ask. But one of the questions that's really interesting to me is what determines our weather here in the mid latitudes where we live. We live in the mid latitudes, sort of between, say, like 40 degrees and 70 degrees latitude. All right. And we see these weather systems pass by. You go from fair weather to cold and rainy weather, and then we get heat waves and cold spells and so on. And we also know that anthropogenic climate change is going on at the same time, and we wonder how that's going to affect our weather. So that's the general area that I'm interested in for my group. And what we use to study that, to a large extent, are models. And those models are typically, not always, but they're typically computer models that include really simplified atmospheres where you just have basically the planet is treated like a billiard ball, and you just have a layer of gas around it, and you can simulate its motion, right? And then you can add in effects like clouds, moisture, mountains, oceans, and terrain and so on. And as you add in these different effects, you come to the point where you can actually simulate how carbon dioxide concentrations can affect the atmosphere's temperature and also the motions in the atmosphere. And those models that include all those effects are called climate models or global climate models. And we use those to study how climate change is operating on our planet at the current time. Yeah, so we use these models, and there are large software packages that are made by groups that focus on the development of the best ways to represent the atmosphere in a computer. Right. So when you take computational physics, you'll learn a lot. If I hope you take that course, it's a great course, 407. If you take that course, you'll learn a lot about how you can use different numerical methods to solve problems in physics. And one of the things you can use computers for is to solve the equations of fluid motion, and also the equations of transfer of electromagnetic radiation through the atmosphere. So we use computers to capture the Navier-Stokes equations and approximations to those equations, plus to capture radiative transfer and various other kind of physical processes, plus chemical processes and so on. We can try to combine them all into these global climate models, GCMs. And that's what we use. That's what we use to study the atmosphere, in addition to all the observations we have. Observations play a huge role in atmospheric science. We have a ton of data, and our field really has a big data challenge to it. We continuously gather data from satellites and weather stations and balloon launches, and bringing that data into our models is a big part of the work that takes place actually in our in the group of people who study atmospheric science at our department. So in my own group, we focus on the models and how to analyze them and different experiments you can do with them For example, I don't know if you want me to go into this detail now, but the kind of things we do, for example, would be to take a model and change it in some way. So, for example, we could ask, all right, well, in some years we see, a greatly enhanced snowfall in certain regions. What does that snowfall do to the weather in other regions? And so we can actually study the impact of imposing a snow patch, a large snow patch, several thousand kilometers on a side, on the larger atmosphere. And this is motivated by observational work that people have done to study how the atmosphere responds, how the atmosphere appears to behave after some sort of large snowfall event. That's just an example of the kind of thing we can do. Most of my work has been focusing more on the problem recently of sea ice and sea ice loss. Do you know about the Arctic sea ice and what it's been doing lately?
I'm guessing melting.
I was guessing they're just melting.
That's right. So there's a lot of interest in two things, kind of two sides of the coin. One side is what is causing the sea ice to melt, and the other is when the sea ice melts, what else does that imply for the atmosphere and the ocean? And so for the first problem, what is causing sea ice to melt, we can largely point our fingers at the impact that human beings have had through greenhouse gas emissions and greenhouse warming. That drives a lot of surface temperature increase, and it has this big impact on the polar ice, involving positive feedbacks and things you might have heard of before. But that's not the whole story there, because you can also get some sea ice loss happening just spontaneously. Some years you'll lose sea ice, some years you'll gain it back. And our models actually simulate that process as well. But the other side, which is, well, when the sea ice changes, what does that mean for the rest of the atmosphere? Well, that's a much more theoretical question, because sea ice is part of the climate system. So when we do a computer simulation where we impose a change in sea ice, we're kind of playing with nature, right? But we're doing it all in the computer. But we found we've learned a lot from doing those kind of specialized experiments, because we learned that, in years where there's reduced sea ice, that actually has impacts on weather and climate in distant regions away from the atmosphere, away from the sea ice regions. And it also has impacts on the ocean as well. So one of my PhD students is just finishing off her PhD in this area, Stephanie Hay, and she's finding that, in fact, even changes in sea ice in Antarctica, like the Antarctic sea ice, can have impacts on the climate of the northern hemisphere where we live. And you need computers to do this, because these are not things you can do in nature. You can't really go and do a controlled sea ice loss experiment where you remove all the sea ice from Antarctica. You couldn't get away with it, and you couldn't do it anyway. It's too much of a challenge, and you wouldn't want to do it, right? But with this, what we're really asking here is if we see these predictions of sea ice change, and we want to understand, want to use the computer to better understand how the whole climate system operates, so we can have better predictions and also understand it at a deeper level.
I'm not gonna lie, I don't think I've ever actually been this interested in atmospheric physics, because I've always thought of it as just let me be a little objective before I get into the reasoning. But in the beginning, I was actually not a big fan of it, because I was always like, science is about physics, especially about space, about discovering the universe. Why focus on the Earth? But like, as you're describing it, there's some really cool things that I never knew were possible, especially with the Navier-Stokes equations and stuff. So I think it's giving me a real big realization of atmospheric physics.
Well, good. That warms my heart.
Thank you.
But really, honestly, that's the amazing thing about physics and math too, for that matter, is that we kind of learn the tricks and the tool, the skills to analyze many different types of systems. You have to be really careful when you do it, because you can get a little you can sometimes what's the right word, get a little arrogant and think, I can study anything because I've studied physics. But the fact is, that's not totally true, and every field has its own areas of kind of specialization. But as an undergraduate in physics, you get the training you need and the analytical skills to kind of get into these other fields. And that's was a real privilege for me to realize, that I was able to actually take my physics education even one step further and get an atmospheric physics specialization and still be in touch with all my colleagues in physics, right, and learn from them. So yeah, no, great.
Mm-hmm.
I think the important thing is to keep an open mind, and,
Yeah.
and you never know, like stellar dynamics, as there's a lot of fluids in it, there's a lot of turbulence, and so you never know what you'll learn in any sort of fluids course will benefit you later on.
Mm-hmm. I had a question. When you study like sea ice and the atmosphere and everything, do you take into consideration the orbit of the Earth and its I think it's called obliquity, like the angle of depression off
Yeah.
of
I'll just correct you on one thing: obliquity.
Obliquity.
Yeah, you're really
obliquity,
close, though,
right?
Parker. So that's good. No. So when it depends on the problem you're interested in. So I tend to focus on problems of what's happened over the recent decades. So not such long time scales, but if you're interested in the impact of orbital variations in obliquity and the migration of the axis of rotation over different time periods, then you get into thousands and thousands of years of past history. And what that gives you an opportunity to do is look at the what's called the paleoclimate record, the record of past climates that extends back, of course, the several billion years of the Earth's age, right? And you can try to understand in the geological and fossil record how oceans and the atmosphere were varied over the years. And in those situations, sea ice and especially glacial ice are very, very strongly influenced by orbital parameters. And so, yes, you definitely have to worry about that, but not in my problems. My problems have focused much more on the recent decades because that's kind of where I end up focusing most of my attention. But the past climates are really, really interesting as well and give us lots of food for thought.
Yeah, I took a course second semester. It's called Ancient Civilizations and Their Environment, and we touched on, well, we didn't go into like the physics of everything, of course, but we touched on like glaciers and how you would take like how you would do carbon dating with ancient ice, and as well as the Earth's position relative to the sun and everything, and how that affected the environment.
Yeah. So how many years have you been like experimenting on the atmosphere? Let's word it like that.
Yeah. Well, I'm not an experimentalist. I'm very much
sorry. But
no, that's
sorry.
okay. I knew
not
what you meant.
wrong word, but yeah, you know what I meant.
In air quotes. I know I was putting in air quotes, but just for anyone else, no. So I've been working in atmospheric physics. I started as an undergraduate with a summer position, and I graduated in 1990. I guess I started in 1988, and basically that's what I've been working on for all this time. I know it's a long time, 30 years.
Wow! So in those 30 years, what is the craziest thing that you and your group or you individually have discovered? Or like seen, or something that's just blown your mind, just in general.
Right. Well, after I graduated here from the University of Toronto, I spent several years at the Geophysical Fluid Dynamics Laboratory in Princeton, New Jersey, which was GFDL. And while I was there, I postdoced there for a while. I was a postdoctoral fellow, and then I stayed on as a research scientist. While I was there, I started to work on models of the atmosphere and how conditions in the upper atmosphere influenced conditions at the surface. And one of the things we discovered, which was kind of crazy, was that you could heat the air or cool the air way up in the stratosphere, which is actually several kilometers above the surface of the Earth. And we found that in this model, which was stripped of a lot of detail, that we could actually change the jet stream a lot just by cooling off the Arctic stratosphere. So I know that might be a lot of jargon, but what we're talking about is here we're cooling off a very small amount of matter, up in the up at like zero point 0.1 atmospheres, that kind of, or zero point 0.5 atmospheres, really not very close to the ground at all. And we had this outsized effect on the jet stream in the troposphere. And it turned out, and the reason we studied this problem in a really simple model was that people had been noticing that as a result of climate change and the loss of ozone, ozone in the stratosphere, there seemed to be impacts at the surface that could be observed. And what we found was that we could actually get these impacts really strongly in this pretty simple model. And that discovery was really exciting for me and for my colleagues. And we wrote a lot about that effect, and I found that really, really interesting. And then understanding how that worked, like how the role of atmospheric waves and driving that change. It's actually still a topic that people study a lot today. I actually have worked less in that problem on the role of the stratosphere in the climate of the surface, but it's still very interesting and a pretty active topic of research. I would just add one more story that what I really learned when I was working in this laboratory was how, science now operates in a way that's can often involve like large teams of people, and how fun that can be. So I worked in an environment at this lab that it was a lab of the U.S. government, the National Oceanic and Atmospheric Administration, NOAA, and I came in as a physics grad, but I left as somebody who was really understood a lot more about climate science. And for the several years I worked there, I learned about how large teams of people working on these global climate models can accomplish a tremendous amount if they are able to interact with each other and talk about different disciplinary areas. So it taught me a lot about the value of interdisciplinary work. And with that, I discovered a lot about how global warming operates and how the ocean operates as well. So those were things I learned about in that kind of environment that I wouldn't have learned, just in a physics program. So
that's really
So one of the things I'd say is,
cool.
You can make your own discoveries, but also where you work, the environment where you work, is tremendously important and kind of giving you kind of more exposure to different ideas. And I've taken that lesson with me. I like working in teams. I like working with larger groups of people, as well as working like one-on-one with students and so on.
Awesome. Yeah, I've just been absorbing everything you're saying. Yeah, but it's all really like really interesting stuff. So yeah, we're coming up on to the later stages of the podcast. Sure. We do have a lot more questions to ask you.
Yeah.
So maybe we can have you on another time if that works.
Sure. Happy to come back in.
I was thinking of something. Yeah, sorry. I was thinking of something crazy, something really. I mean, it would be a lot of fun if we can pull it off. But when school starts, hopefully, if Parker can come down from Ottawa, you, me, Dr. Kushner, and Dr. Julian can have like an hour and a half podcast. I'm saying that would be really cool.
That would be
like
crazy.
We can talk about. Because he's condensed matter, you're atmospheric, so we can talk about, quantum mechanics, we can talk about macromechanics, we can talk about a lot of stuff. So
sounds great.
I think that would be a cool idea.
Sounds like a good classical quantum smackdown. That'd be great.
Yeah.
sounds like a lot of fun.
Yeah.
Yeah. No, I enjoy talking to Professor Julian too. So that would be fun. Thanks very much.
That would be fun. Absolutely.
Yeah, thank you so much for coming on today. This was an absolutely fascinating conversation, and I surely learned a lot.
Great. Well, it was really nice talking to you guys, and I appreciate that you're doing this, and I wish you the best of luck for the coming year. And let's keep in touch.
Yeah,
absolutely.
Thank you so much.
Thank you so much for coming on.
Okay.
We can sign off now.
Yeah, so this has been episode number 25 of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we will see you soon.
See ya.